Hello and welcome to my talk, SQHell, Embracing and Avoiding SQL Strangeness. I'm Tiberius. I've been a pen tester for over a decade, though the vast majority of that has been focused on web application security. In the last few years, I've been creating cybersecurity content in the form of YouTube videos and Twitch streams, mostly aimed at people wanting to get into web app testing. Prior to that, I created 2 privilege escalation courses for the OSCP, which is still pretty popular. And creating those unlocked a passion for educating the next generation of cybersecurity. Other than that, I created a popular tool called AutoRecon, which can be used to enumerate services on networks. I also have less popular tools in the form of burp extensions. There are pretty much too many social networks these days, but I try to maintain a small presence on most of the major ones. You can visit my link tree on the screen and find me at your favorite if you like. If you follow me on Twitter, or X as it's now called, you may see several quote-unquote hot takes about SQL, among other things. These include why we shouldn't be teaching people to use OR 1 equals 1, and to OWASP and Portswigger's credit, they now either use different examples or put a warning text explaining why it's a bad idea. I'm also a vocal proponent of pronouncing SQL correctly, and not that other way that people seem to enjoy. I also enjoy creating fun stickers for conventions, and I usually have quite a few with me, so if you do see me at a convention, please come up and grab one. So I think it's probably important to address the question of why we're still talking about SQL injection. One of the YouTube comments I got last year raised some good points. Aren't nearly all SQL injection vulnerabilities countered by using parameterized queries, and hasn't that been the standard for many years now? They are correct. Parameterized queries, aka prepared statements, counter pretty much all SQL injection, and their use has been standard advice for over a decade. There are, however, a few external factors at play. There are still some developers who either aren't aware of SQL injection and the danger it poses, or they are using unreliable countermeasures. Even when modern frameworks provide developers with quote-unquote safe ways to interact with the database, like ORM, there are generally ways around this. ORM is great in a lot of simplistic cases, but when it comes to complex operations, it can get a little tricky, and developers may be tempted to use raw SQL instead. Finally, possibly the biggest reason, there is still just a lot of legacy code out there. So what do I mean by SQL strangeness? Well, SQL is a rather strange language in of itself. Despite being a standard adopted by most relational databases, the only really standardized part of it seems to be the general structure of statements. So for instance, select column name from table name, where column name equals some value, is about as far as you can get when trying to write an SQL query that works on all SQL database servers. They each implement the language differently, often making changes or even additions to things you would expect to be standard. We have the more obvious differences like function names. To calculate the substring of a value in MySQL, Postgres, MS SQL, and SQLite, you can use the substring function. But in Oracle, you use substra, and also SQLite has an alias for this too. We then have functions with the same name that do different things. For example, the length function in MySQL counts the number of bytes in a string, so giving it the Unicode rocket emoji produces a length of 4. However, the same length function in Postgres, Oracle, and SQLite counts the number of characters, producing a length of 1. Most of these databases have other length functions that do the opposite, but it's still a strange design decision and ultimately can lead to confusion. Then we have limiting and offsetting results. Say we have a query and we only want to show the 5th row of results. In MySQL, Postgres, and SQLite, this is accomplished very easily. Select all from users, limit 1, offset 4. In MS SQL, you have this mess, where you first need to order the results by a column and then use an extremely verbose syntax to get what you want. Select all from users, order by name, offset 4 rows, fetch next 1 rows only. The same is true for Oracle as well, although thankfully you do not need to specify an ordering. So the purpose of this talk is to share with you the more complex examples I've come across. Some of them are just good to be aware of so you can avoid them messing up an SQL injection attempt. Others are just kind of interesting quirks that are really only useful in CTFs. My final example is likely to have caused and continue to cause quite a few exploitable SQL injections for years to come, and the strangeness doesn't technically relate to SQL per se, but leaving it off the list seemed like a bad idea since I'm not actually sure how many people are aware of it. If you work in bug bounty or web pen testing, I would definitely hunt for this vulnerability when you can. They also don't take credit for finding these originally, and maybe you're aware of some already, maybe you know them all. Hopefully there will be at least one that will come as a surprise. Also, fair warning, like the biggest offender in these cases is MySQL for some reason, take from that what you will. Okay, so the first example of SQL strangeness is more of a way to use certain SQL behaviors to bypass other SQL requirements. This was the result of a friend of mine reaching out to me after encountering a simple SQL injection, which appeared to be breaking whenever a comma was used in the payload. Some server-side filtering was clearly in place, and unfortunately this meant a union injection couldn't be used to easily extract information. So with a union injection, you create a secondary query, which must contain the same number of selected columns as the query you're injecting into. So in this case, the original query is selecting 3 columns, ID, name, and age, which means our union injection must also select 3 columns, though these can actually be numbers, strings, or function calls like version. Since selected columns are separated by commas, we needed a way to do this without them. And after some research, we identified a potential method. The solution was to build a single table in memory, which consisted of multiple one-column tables joined together. To explain, if you run the simple SQL statement select 1, a pseudo table will be created in memory with a single column labeled as 1 and a single row with 1 as a value. These tables exist for the duration of the statement, but we can create them inline and use join to effectively concatenate them together into a single table with the required number of columns. So here we are selecting all from and then select 1 as A joined with select 2 as B. The only caveat is we need to also give each pseudo table a unique alias, that's the as A and as B, but that's quite simple. In the end, our union injection ended up looking like this. So provided we use a select all from and then pass in our string of joins, we can create a table with an arbitrary number of columns and containing rows of whatever data we require, all without using a comma. In this example, we're extracting the version number of the database, but we can replace that select version query with another select and reliably extract any data we want from the database. SQL injection without spaces and inline comments. So if you hack enough web apps, you'll eventually encounter SQL injections where the developer has tried to thwart attackers by rejecting strings with spaces in them. In most cases, we can get around this by replacing spaces in the syntax with inline comments, using the hash symbol instead of the standard double dash space at the end. If for some reason we do need a string in our injection to contain a space, we can usually encode it and run it through the appropriate decoding function within the SQL. For example, in MySQL, we can encode our string to hex and then use the unhex function. If we cannot simply comment out the rest of the query, we can break back into the original structure. I feel like this is a pretty commonly known about bypass, but what if developers also rejected forward slashes and asterisks? Well, it turns out that in MySQL at least you can get pretty creative with parentheses. For example, this union injection can be replaced by the following. Since the original injection was an integer, we need to surround it with parentheses as a way to separate it from the union operator. When selecting columns, we technically only need to surround the first and last with parentheses since they quote-unquote touch the select and from keywords. In case it isn't clear, pretty much all parentheses line up with the next one apart from the one after the union, which surrounds the entire select as seen here. Similarly, if we're injecting into a string, we can use a slightly modified payload. MySQL type juggling or type casting. Okay, so this one surprised me, and as far as I'm aware, MySQL is the only database to do this, or at least to the extent that it does. There is some backstory to this one. Last year I created a room on TryHackMe designed to teach people the dangers of using or1=1 blindly in SQL injections. The room consisted of a simple login page and no credentials were provided. The username input was insecurely passed to an SQL query using the username parameter. The login code, however, checked to see if only one row was returned, so it wasn't possible to use a simple or1=1 injection, as that would cause every row of the users table to be returned, and there were multiple users configured. However, to be extra evil, the username input was also insecurely passed into a delete statement. The flags table contained the only flag needed to complete the room, and would only delete the flag if the flag matched the username input, unless the user was careless with their SQL injection. If an or1=1 or equivalent, i.e. an or true, was injected into the username field, this would cause the delete statement to delete the flag, and the user would be presented with an obnoxiously large and red fail message telling them they had to restart the entire machine to get the flag back. Everything was working nicely. There were a few minor bugs and unintentional bypasses that some clever people found, but then one of my friends messaged me saying he managed to trigger the flag deletion using an oddly simple payload, which at first glance did not appear to be malicious. That's literally a single quote, the minus sign, and a single quote. So when that string is set as the username, we get the following SQL query: delete from flags, where flag equals 2 single quotes minus 2 single quotes. We end up with an SQL statement where it looks like we're subtracting an empty string from another empty string. So I imagine there's a few people here who have realized what's going on, but I eventually realized once I played around in dbfiddle. Now, while other databases might throw an error here because clearly subtracting a string from another string makes no sense, MySQL tries to be clever and make it happen anyway. MySQL knows that numbers can be subtracted from each other, so it converts both strings into numbers. Now, in MySQL, as in a lot of languages, most strings are equal to 0. The exception is when the string starts with a non-zero number. For example, 1test is equal to 1, and 0.4 ASDF is equal to 0.4. This is known as type juggling or typecasting, and it can lead to some weird bugs and even exploits. Okay, so with my friend's payload, an empty string is equal to 0, so 0 minus 0 results in 0. We can simplify the SQL statement to delete from flags where flag equals 0. But wait, the flag is a string and we're comparing it to an integer, so why did it get deleted? Oh, it's converting the flag to an integer, isn't it? Yes, we have type juggling inside of our type juggling. We have type juggling inception. So the flag started with a capital T for try hack me, which of course isn't a non-zero number, so the entire flag got converted to the integer 0 for the purposes of the comparison. And since 0 does indeed equal 0, the conditional check on the delete statement was upheld and the flag was deleted. Now, as it happens, this is also the case in MySQL if you use the plus operator to try and add two strings. So some lessons we can learn from this. Is this as dangerous as an or 1 equals 1 injection? No, but it's probably best to avoid using payloads that look like this, especially if you know the database is MySQL. There are of course plenty of quote-unquote safe SQL injection payloads you can use instead, and as far as I'm aware, SQL Map never tries to use these payloads, even if you set the risk equal to 3, although it does start using OR-based payloads at that point. Okay, let's talk about MySQL in Node.js, specifically prepared statements. If anyone is unsure of what prepared statements are, they're basically some database magic which prevents 99.99% of SQL injections and are generally pretty easy to implement for developers. So in this before example, we are passing a user input variable in red directly into the SQL query using concatenation, and this is what leads to the SQL injection. In the after example, we have a separate statement with a placeholder question mark where we want our variable to go, but we pass this variable to the database separately. The database understands the difference between what should be query structure and what should be input data, and this effectively renders injection impossible. It's important to note at this point that prepared statements are the most recommended mitigation technique for SQL injection, and every language usually supports it. So, Node.js lacks native MySQL support. If you use npm to install the MySQL package, it will install one which has around 1 million weekly downloads. The source code for this package is available on GitHub at the URL on the screen. Now, if you scroll all the way to the very end of the README file on GitHub, you'll find a to-do section with a rather interesting bullet point. Yes, as it turns out, the most popular MySQL package for Node.js, used by over 7,000 other packages in npm alone, does not actually have prepared statements. You'd be forgiven as a developer or even a code reviewer for that matter if you didn't notice, however, since the documentation includes examples like this. This looks eerily like a prepared statement, but the description of the function does state that this is a client-side escaping function, and further notes that this module will escape based on the shape of the passed-in JavaScript value. This is honestly just a kind of weird way of saying that escaping is based on the data type, e.g. integer, string, date, etc. Okay, so this is actually fine when the values being passed are strings, booleans, integers, dates, etc. In fact, for almost every data type you pass to be escaped, you end up with a properly escaped value in the resulting SQL statement. It's still not prepared statements, but you can't break out of a string and inject raw SQL. So what isn't fine? Objects. Object escaping is broken, or at least It kind of makes sense from one perspective, but introduces a novel SQL injection technique in another. Here's a simple JavaScript object with a key called ID and a Boolean value of true. Here's what you get if you escape that object, i.e. you pass it to the query function. The backticks denote that the string should be treated as an identifier. In other words, it refers to a specific database, table, column, etc. The intention being that you can pass objects directly into update statements if you want to update arbitrary columns. So what happens when we have a select query and pass the object as a value used in a comparison operation? Well, you end up with this interesting string being sent to the database, where ID equals true. It turns out MySQL can handle this comparison and it effectively resolves it left to right. So it will first check that the ID column is equal to the ID column, and of course that's always true, so we can just simplify this to true equals true. Assuming we send this object to the application and have it be passed to the query, we can turn this query, which should return a single row, into one which returns all rows. Now in this example we do need to know the name of the column, however, it turns out we can flip the logic, provided we know or can guess any other column name. For example, if we pass an object with the username key set to the Boolean value false, this results in an escape string with a comparison where ID equals username equals false. Again, if we read it from left to right, we check if the ID column equals the username column, which in most cases isn't going to be true, so we get a false. We then end up with a false equals false, which is of course true, and once again, we return all rows. Luckily for us, Node.js applications often use JSON when submitting data to the server, for example, when users submit a form. JSON, of course, stands for JavaScript Object Notation, and a JSON object is essentially a string representation of an actual JavaScript object. When Node.js receives JSON data via request, it will create a JavaScript object out of it. If parts of the object are passed directly to the query function without the type being checked, it may be possible to perform this SQL injection. Even more luckily, it turns out that Node.js, or more accurately the Express framework, also recognizes HTTP array parameters popularized by PHP and helpfully converts them to objects too. So for example, if you append an ID in square brackets to the end of a parameter name, in this case name, and give that parameter a value like 1, you get the following JavaScript object. Since the server-side code was expecting a parameter called name, when it extracts the value of this parameter from the object, we get the embedded object instead, and the attack continues like before. So there is a potential authentication bypass here too, assuming that passwords aren't being hashed, which I understand is getting less and less common. However, it's worth going over and demonstrating, because ultimately the biggest drawback of this injection technique is we really cannot do anything complicated like union injection or even use comments. So we have a query that looks like this, and we pass this JSON object to the web server. We set the username attribute to the user we're targeting. We set the password attribute to a JSON object itself with a password attribute set to the Boolean value true. The resulting query that gets sent to the database checks whether the username is admin and whether password equals true, which is always true. The outcome is we get logged in as the admin user. We can also use regular post parameters like the following and get a slightly different query, but ultimately one which resolves in the same way. Okay, so I pre-recorded a video of this, but if you want to play around with it yourself, you can find the code on my GitHub. It's forked from another repo, so I can't claim credit for the initial code, but my version has debug statements enabled, which means we can see what types our inputs are cast to, and also see the SQL statements that are sent to the database. Okay, so here we're just using a login form to log in as the admin, but we get the incorrect password. We go to burp. You see this is just sent using regular body parameters, and in the logs you'll see that the username, admin, password both are strings, and there's the query that gets executed on the database. Okay, so we're going to use burp to send this to repeater, and again we just send it, we get that incorrect username or password error message. So now what I'm doing is manipulating the password field to turn it into an array parameter and setting it to 1, and we get this redirect, right? So actually technically we're logged in now. And we see here the username is still admin, it's still a string, but the password is now an object. And there's password equals 1, so basically an and true, and it returns 1 row. which is the admin user. So it's currently form encoded. So if we change it to a JSON object, basically we just have to supply a valid JSON object where the username is equal to the string admin again. And then the password field, we're going to create another JSON object. And we're going to set password attribute of that object to true. And again, we get this redirect. Basically, we've logged in. We check the logs again. Username is still a string, but the password again is an object. And we get roughly the same thing. Password equals true.